you for joining me. Today I would like to discuss a paper by Li, Xu and Sun on autonomous orbit determination for satellite constellations, which are all the rage nowadays. So orbits in satellite constellations are usually fixed by design, but over time the position and velocity of the satellites starts to differ from their original values. And to estimate the real values, then what we usually do is we communicate either with the Earth or with a satellite network, such as GPS, for example. And when that communication fails, the constellation is left pretty much on its own. It doesn't have any data to resort to. So the question that the authors pose on the paper is it possible for a constellation to autonomously determine the position and velocity of all of its satellites? And to do this, what they do is they design their own constellation and their own method, and they test it, as you will see. This is their constellation model. It is a hybrid constellation containing remote sensing satellites in low Earth orbit, or LEO, and communication satellites in middle Earth orbit, or MEO. There are two data sources for orbit estimation. One of them is the camera that low Earth satellites carry that provides images that can be used to track specific landmarks such as rivers or oceans on Earth. And the other one is the laser altimeter, which all the satellites carry, and that provides height information and also ranging, that is distance between satellites information. And these three measurements are then fed to an extended Kalman filter, which is an estimation algorithm very commonly used in satellite control. So with this structure, the authors define two use cases. First of them without ranging, only for the low Earth satellites, and second with ranging for all the satellites in the constellation. And they also define two failure cases, one of them in which half of the cameras failed, and then the other one in which on top of that half of the altimetry failed. So the idea was to test the algorithm for these two cases. Okay, and here is what they achieved. Now, as you see, of course, it's not a perfect estimation, and not all of the hypotheses were proven true. Because, for example, the authors assumed ocean altimetry to be better than land altimetry, and the opposite turned out to be true. And another problem was that optical images were not available at all times because of atmospheric conditions, because of the night-day cycle, and only a few images could be used to track features on Earth. But overall, the algorithm does provide a robust estimation of position and velocity, and that works both in nominal cases and in failure cases, even though in failure cases the performance is logically worse than in nominal cases. So I think this research is quite promising. Of course, it has its limitations. The main one that I can think of is that it's performed on a simulated environment, so the conditions in the simulation are not going to correspond to the conditions in a real environment, and we really have no way to know if this algorithm could work as well as it does now on a real constellation. Perhaps it would be good to do some research on existing constellations with similar characteristics and test if the algorithm could be applied there. But the concept, the fundamental concept, is very interesting, and I think it's worthwhile exploring. I like this idea of fully autonomous satellite constellations, and if you find it as interesting as I do, then you might want to check out the link in the video description down here and read the paper for yourself, which is in open access. So thank you very much for watching, and have a lovely day.